Why waste time in commute and spend lot of money for iitjee coaching? Parents, do you want your kids to achieve top scores in iitjee? India's leading online NEET coaching 100% success iitjee. At TeenEinstein, we focus on iitjee coaching from class 6 to class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for class 6 to class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
In the previous video, we talked about the capacitance for a parallel plate capacitor. We derived it as C equal to epsilon 0 A by D, where A is the area of the plate and D is the distance between them. So what we are going to do now is we are going to put a dielectric in between the plates of this capacitor. So first let's assume that there are two large plates, just like we saw in the last video, and each of the plates have area A and they are separated by a distance D, and each have the charges plus or minus Q on them, and there is vacuum between the plates. When there is vacuum between the plates, then the electric field between them is equal to sigma by epsilon 0, where epsilon 0 is the permittivity of the vacuum. Then we will derive what is V0. V0 is the potential, which is equal to E0 in multiplied by D. So the capacitance E0 equal to Q divided by V0, which is equal to epsilon 0 A by D. So this is what we derived in the last case, and now the subscript 0 here is added because to represent that this is the case where there is vacuum between the plates. Now we are going to put a large dielectric between the plates. So when there is a dielectric inserted between the plates, that is fully occupying the intervening region. So there is no air gap or anything. So the dielectric is fitting right into the between the plates. So we already talked about what happens when a dielectric is put in between the field. Then there is polarization that is happening, and because of the polarization, there are surface charges that are created in the inside the dielectric. So in left side we have sigma p and minus sigma p, and the right side, which is the induced charges. So these are the bound charges. We already studied this. So when you put a dielectric in between the plates of a capacitor, it means that the surface charge densities on the capacitor plates now become from sigma to sigma minus sigma p, because the net charge will become sigma minus sigma p and in both the plates. So the charge now becomes plus or minus sigma p on the plates. Now we know the charge, so we will calculate what is the electric field. So the electric field equal to sigma by epsilon 0. Instead of sigma in the previous case, now we have sigma minus sigma p divided by epsilon 0. And now instead of V0, we have V, which is equal to E multiplied by D. And E here is sigma minus sigma p by epsilon 0. So V equal to sigma minus sigma p by epsilon 0 multiplied by D. So now we know V, then the next step is to calculate the capacitance. So before going into that, we will simplify this a little bit. So for linear dielectric, sigma p is proportional to E0. So why sigma p is proportional to E0? E0 is the field that is created, and this is the field in which the dielectric is kept. So if this field is higher, then sigma p, the polarization is also going to be higher, so the surface charge is also going to be higher. So the sigma p is proportional to E0. And let's look at where is this E0 coming from. E0 is coming from the capacitor plates. So if there are charge sigma on the plates, then that charge is going to control how much is this E0. So in a way, sigma p is proportional to E0 and also to sigma because of that. So if sigma p is proportional to sigma, then the difference, that is sigma minus sigma p, should also be proportional to sigma. So that is the conclusion which we derive from this. So if sigma minus sigma p is proportional to sigma, we will add a proportionality constant called 1 by k. So this term sigma minus sigma p is proportional to sigma, so you add a constant 1 by k. And let's substitute this in the potential difference now. So when we had sigma minus sigma p multiplied by d by epsilon 0, instead of that we will substitute sigma by k. So we have sigma d by epsilon 0 k, and sigma is nothing but q by a, that is because of its a surface charge density. So we have q d by a epsilon 0 into k. So this is the potential. So now what is the capacitance? Capacitance is q by v, right? So let's substitute this v here in this equation, q by v. So then if you substitute qd by a epsilon 0 k, and the epsilon 0 k goes to the numerator, qd comes to the denominator, and q gets cancelled. So you have epsilon 0 k a divided by d. So this equation is similar to C0. C0 is nothing but epsilon 0 a by d. So the only difference is the factor k here. So the product, let's assume that this product epsilon 0 k is the permittivity of the medium, and we can denote this by the symbol epsilon. So the quantity epsilon 0 is the permittivity of the free space, and epsilon is the permittivity of the medium. So epsilon equal to epsilon 0 multiplied by k. So let's see what happens. So then what will be k? K equal to the ratio between epsilon divided by epsilon 0. So this is called dielectric constant of a material, which is nothing but the ratio between the permittivity of the medium divided by and the permittivity of free space. So this is the only difference between the capacitance of the parallel plate capacitor when there is vacuum and when there is dielectric. So the ratio k equal to C divided by C0. So it's very obvious that when you put a dielectric, the capacitance of the capacitor actually increases by a factor of k. So C0 is the capacitance when there is vacuum, and C is the capacitance when there is dielectric. So obviously C equal to K multiplied by C0. So this gets multiplied by the factor K. So if you want to increase the capacitance of a capacitor, you can just insert a dielectric in between. So K is called the dielectric constant of a material. The capacitance increases by the factor of K when a dielectric is inserted between the plates instead of vacuum. Okay, so now we already talked about parallel plate capacitor. We derived the capacitance of a parallel plate capacitor, and then we derived the capacitance when there is dielectric. Now we are going to use these capacitors in combinations, like in series and parallel combinations. So several capacitors with capacitance C1 to Cn can be used together to get effective capacitance of C. So we will just put this capacitance in series. So this is the series combination. So in series combination, what you do, you have parallel plate capacitor, two parallel plate capacitors with capacitance C1 and C2, and they have to have the same charge on the plates because they are connected end to end. That means the negative plate of one capacitor is connected to the positive plate of the other capacitor. So if this Q is greater than this Q, then the charges will redistribute themselves until the charges are equal in both the plates. So then that means in a series combination, the Q has to be same in all the plates. So all the capacitors have to have the same charge on them. So this is the case for series, and let's see how to calculate the overall capacitance or equivalent capacitance of this particular configuration. So the total potential drop V across the combination is the sum of the potential drops V1 and V2 across C1 and C2 respectively. So the total potential of this configuration is V1 plus V2. So let's write it like this: V equal to V1 plus V2, and from the definition of the capacitance, we know V1 equal to Q by C1 and V2 equal to Q by C2. And the Q is same, so we can take Q outside this bracket. So it will become Q multiplied by 1 by C1 plus 1 by C2. And if you take the Q to the left hand side, then we have V by Q equal to 1 by C1 plus 1 by C2. What is this V by Q? V is the overall potential difference, and Q is the overall charge or the charge of this equivalent configuration. So we can assume this whole whole structure as one capacitor with one charge plus Q and minus Q here, right? So this is the equivalent charge. So V by Q, which is nothing but 1 by, since C equal to Q by V, V by Q can be written as 1 by C. So 1 by C is nothing but the equivalent, C is nothing but the equivalent capacitance. So 1 by C equal to 1 by C1 plus 1 by C2. So this is the case for two capacitors in series combination. So if you have n capacitors in series combination, then we can just add them like this: V equal to V1 plus V2 plus etc. up to Vn. Then we can write Q by C1 plus Q by C2, and you take Q outside and bring it to the left hand side. Then you have 1 by C. 1 by C equal to 1 by C1 plus 1 by C2 etc. up to 1 by Cn. So if you have capacitors in series combination, 1 by C, the equivalent capacitor, equal to 1 by C1 plus 1 by C2 up to 1 by Cn. Okay. The next case, we will put the capacitors in parallel. So when we put the capacitors in parallel, what we do is we connect the positive plates, all the positive plates, and all the negative plates together. So in this case, it doesn't necessarily mean that the charges have to be the same. Charges can be different, but the potential have to be same. Why the potential have to be same? Because the ends are connected by a metal, and metal is equipotential, right? So this, at this particular point, the potential has to be same everywhere in this. So this plate and this plate will have the same potential difference, V. So the potential difference between the plates is given by V, but the charges can be different in this case. So when the capacitors are in parallel, so the charges are on each plate is Q1 and Q2. So Q1 equal to C1 multiplied by V, Q2 equal to C2 multiplied by V. Note that here we are not writing V1 and V2, it is just V. So the total charge on this particular configuration has to be equal to Q equal to Q1 plus Q2. So let's expand this. Q is the total equivalent charge, right? So that can be written as C multiplied by V. C is the equivalent capacitor, V is the potential difference, which is equal to Q1 is nothing but C1V. Q2 is nothing but C2V. So we can take V as common and we can cancel it out. So what it gives you is C equal to C1 plus C2. So when in parallel combination, you just have to add the capacitance values to get the equivalent capacitor. So if you have n capacitors in parallel combination, then similarly you can get the total equivalent capacitance as C equal to C1 plus C2 plus C3 etc. up to Cn. So this is the capacitors in parallel. Okay, so now we are going to talk about energy stored in a capacitor. So when we say energy stored in a capacitor, we mean that what is the work done in arranging this capacitor. So what do I mean by this? If you have a parallel plate capacitor, you have charges plus Q here and minus Q here. To arrange these charges in such a way, to have this particular capacitor configuration, you should have put some work, right? So that work is the energy stored in the capacitor. So how do we do this? First, let's take two plates. There is no charge. So initially the charges is going to be 0. And the final charge is going to be plus Q on this plate and minus Q on this plate. So to bring the capacitor from 0 to Q charge, we are going to do some work. So that work we are going to divide in small steps. So how we are doing is, at every step we are going to bring delta Q dash amount of charge from the negative plate to positive plate, right? So we are starting from 0 and we are taking delta Q dash charge at every step, and we are going to assemble this particular configuration. So to start with this, we will stop in between from 0 to Q, and in between, when the charge on this plate is Q dash and the charge on this plate is going to be minus Q dash. In the next step, we are going to bring delta Q dash charge from this plate to this plate. So then this plate will get the charge, the final charge on this plate will be Q dash plus delta Q dash. Similarly, this is going to be minus of Q dash plus delta Q dash, right? So what is the work done in this one small step from Q dash to Q dash plus delta Q dash? So the work done can be written as V dash multiplied by delta Q dash, because we know work done equal to potential difference multiplied by the charge. So here the potential difference is V dash and the charge is delta Q dash, right? So V dash can be written as Q dash divided by C. So this is the work done in this one step. So remember, listen carefully. The charge on this plate is Q dash and the charge on this plate is minus Q dash. To bring the delta Q dash from this plate to this plate, we need to give this much work. We need to do this much work, right? Let's simplify this a little bit more. So this is nothing but a plus b the whole squared equation minus a squared. If you simplify this, you will get Q dash delta Q dash by C. Because if you expand this, you will get Q dash squared plus delta Q dash squared plus 2 delta q dash multiplied by q dash minus q dash squared. So q dash squared get cancelled. Delta q dash squared is very small, so we can ignore this, and finally we will get this from this. So why we are writing this equation in a little bit complex way like this? Because it helps us know that this is the final state and this is the initial state of the charges. Because in this one particular step, before you do this step, the initial state is q dash squared. Initial charge on this plate is q dash, so we have q dash squared here. And the final charge is q dash plus delta q dash square. So the work done in this particular step is equal to 1 by 2c multiplied by the final charge square minus initial charge square. So if this is the work done in a small step, then we will expand this over all the steps. So from when we go from 0 to q, we are doing it step by step. In all the steps, we are going to add this work done, and we are going to find out what is the total work done. So the formula is summation over 1 by 2c, this particular factor here, which is q dash plus delta q dash square minus q dash square. So what will happen if you expand this? When you expand this, so remember that this is the final charge, this is the initial charge before the step. So 1 by 2c we can take it out. And what is the first step? First, when we begin the process, initially the charge is going to be 0. That's why we have a 0 here. And after the first step, when we bring delta q dash charge, the charge on the left plate is going to be delta q dash square, right? So that's why we have this step. And the next step, already there is a delta q dash charge. So the final charge is going to be 2 delta q dash. And the initial charge is going to be delta q dash. And similarly, the third step, it is going to be 3 delta q dash square, and minus initial charge is going to be 2 delta q dash. So if you keep doing this, this is the final step. When the final step is there, this is the initial charge. Q minus delta q is the initial charge on the plate, and the final charge will be q. So if you simplify this, finally you will just have this q square factor left, because this delta q dash squared and this will get cancelled. Similarly, this and this will get cancelled, and similarly the next terms will keep getting cancelled, and finally you will be left with this q square minus 0, which is nothing but q squared by 2z. This is very straightforward, because the work done is going to be equal to q squared divided by 2c. That's what we started with, right? So Q is nothing but the overall charge in the capacitor. But how we are achieving this charge on the capacitor is important. We are achieving it in steps of delta Q dash. So the overall work done in assembling this particular configuration is Q square by 2C. And now this is the work that is stored in a capacitor. So now the energy stored in a capacitor is Q squared by 2C, like we saw in the previous case. Now let's substitute for Q as A into sigma, because sigma is the surface charge density. So you have A sigma the whole squared into. Instead of C, we can substitute epsilon 0 A by D. Then in the next step, the surface charge density sigma is related to the electric field between the plates as E equal to sigma by epsilon 0. So instead of sigma, we can substitute epsilon 0 E here. So if you substitute epsilon 0 E here and simplify, then finally you will get this equation. U is nothing but the energy stored in the capacitor as 1 by 2 epsilon 0 E square multiplied by AD. And now if you look at the AD, the product AD, A is the area of the plate and D is the distance. So AD is nothing but the volume of the space in between the capacitor. So volume of the region between the plates where there is electric field. So we are going to define a quantity called energy density. So we have energy given like this, U equal to 1 by 2 epsilon 0 E squared into AD. We are going to define another quantity called energy density, that is nothing but this energy per unit volume. So you bring these two things AD to the left hand side. Then you get small u, that is nothing but the energy density, as 1 by 2 epsilon 0 and E square. So this is the energy stored in a capacitor. This is the energy density of the capacitor. Thank you.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology, for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com, contact 99402 49720.